Section 6.3 continued. In the first part of Section 6.3, we learned how to divide polynomials by long division. Now we're going to use synthetic division, and that is a simplified procedure to divide by a linear factor. This is our procedure to set up and use synthetic division. Number one, we want to eliminate all variables and exponents. We want to make sure, as we have in the previous problems with long division, make sure that you put in a 0 as a placeholder for any missing term. Number two, we want to reverse the sign of the constant term in the divisor. Number three, multiply the first coefficient by the new divisor. We want to write that answer under the next coefficient and add. Number four, we want to repeat that process until you have a remainder. Let's take a look at an example for synthetic division. Our first step is to eliminate our variables and exponents. Here's our dividend. I eliminate the variable and exponent. It gives me a coefficient of 5 for my y cubed. My y squared has a coefficient of 1. I'm missing my y term, but I need a placeholder, so I put in a 0. And then I have my constant, which is a -7. Then I'm going to change the sign of my divisor. My divisor here is y plus 1. It's a positive 1, so I'm going to change that to a -1. If you recall, our standard form is x minus a. And here, for this minus sign to turn to positive, my a must be negative, therefore a -1. That's why we always change the sign. Then I'm going to bring down my first coefficient. I'm going to multiply that by my divisor. -1 times 5 is a -5. And then I add. That gives me a -4. A -1 times a -4 is a +4. Then I add, I get 4. And a -1 times 4 is a -4. And I have a remainder of a -11. Then I can use the values that are not my remainder as the coefficients of my factor, which in this case, I'm going to start always with one term less than the largest exponent. Therefore, this is y cubed. I'm going to start with y squared. So 5 y squared minus 4y plus 4 with a remainder of a -11. Therefore, when I divide y plus 1 into 5y cubed plus y squared minus 7, I'm going to get 5y squared minus 4y plus 4 with a remainder of a -11. Now, I just want to verify that I get the same solution if I use long division. So let's take a look at the long division method. And notice I still get 5y squared minus 4y plus 4 with a remainder of a -11. And this is the procedure we used in 6.3 part 1. Let's take a look at another example. We want to use, again, synthetic division. We want to write the coefficients and eliminate the variables and exponents. So therefore, I have 2, -5. And notice I don't have an x squared, so I'll put a placeholder in for that x squared, which is 0, a -10, and a +8. I change the sign of my divisor. Here, it looks like a -3, but I'm going to use a 3. Recall again that that's x minus a. And there's my minus sign, therefore a must be positive. That's why we changed the sign. Let's bring down our first coefficient. 2 times 3 is 6. Add. 6 minus 5 is 1. 3 times 1 is 3. 0 plus 3 is 3. 3 times 3 is 9. Add them. -10 plus 9 is a -1. And 3 times a -1 is a -3. And when I add, that gives me a remainder of 5. Now we can write these coefficients into my expression. Remember, I start with one exponent less than my highest term. This is 4, so I'm going to write with x cubed. So I have 2x cubed plus 1x squared plus 3x and minus 1. And I also have a remainder of 5. Let's take a look at another example of using the remainder theorem to determine a solution. Here I have a equal 2. Recall our standard form is x minus a. They give us a. That's why I don't change the sign. Therefore, I just bring down the 2, and then I put in the coefficients. Remember, we eliminate the exponent and the variables. Here I have 1 for my x to the 5th. I'm missing an x to the 4th, so I have 0, an x cubed, so I have 0. Here's my x squared, that's a negative 3. I'm missing my x, so I put in a placeholder for that, which is 0, and my negative 20. Now I bring down my first coefficient of 1. 2 times 1 is 2. I add, I get 2. 2 times 2 is 4. I add, I get 4. 2 times 4 is 8. I add, I get 5. 2 times 5 is 10. When I add, I get 10. And 2 times 10 is 20. And when I add, I have a remainder of 0. Therefore, if I would substitute 2 into this expression, that would give me 2 to the 5th, which is 32. 2 squared is 4, times 3 is a negative 12, minus 20. That would give me 0. So again, I just verified my remainder theorem that if I would substitute 2 into my expression, I would have a value of 0. So here, my function, p of 2 equals 0. In this example, I want to use synthetic division and given factor to completely factor each polynomial. So I'm going to use synthetic division. So I have my divisor is a positive 3 in our expression. So therefore, I know my a is negative. So I'm going to change the sign to a negative 3. And I have the exponents of 1. My x squared is missing, so that's going to be 0. I have an x of a negative 7. And I have 6. Let's bring down our first coefficient, which is 1. Negative 3 times 1 is a negative 3. When I add, I get a negative 3. A negative 3 times a negative 3 is 9. When I add, I get 2. And a negative 3 times 2 is a negative 6. And I have a remainder of 0. And recall, what I can do is to write these coefficients in an expression with a term starting 1 degree less than my largest degree in my original expression. So here, x cubed, so I'm going to have x squared minus 3x plus 2. And what they wanted was to have a solution in factored form. To do that, all I need to do is to take this expression and factor it. X, and this would be minus 2 and minus 1. And if I FOILed, that would be x times x is x squared, minus x, minus 2x is a minus 3x, and a negative is a positive 2. Therefore, I know if I would multiply these two linear factors together, I would end up with x squared minus 3x plus 2. And if I multiplied it by the given linear factor, x plus 3, it would give me back my original function, which is x cubed minus 7x plus 6. So if I would completely factor that, that would be my solution in linear factored form. Let's take a look at another example. Again, they want to use synthetic division in the given factor to completely factor. So to do that, I need my a, which in this case, they show a negative 2, but I changed the sign. A is actually 2. And I write the coefficients with eliminating the variables and exponents. So 1, negative 2, negative 1, and 2. I have no missing terms, x cubed, x squared, x, and then my number. Let's bring down my first coefficient, which is 1. 2 times 1 is 2. Negative 2 plus 2 is 0. 2 times 0 is 0. When I add, I get a negative 1. 2 times a negative 1 is a negative 2. And I have a remainder of 0. Now recall, I can write this as an expression with my coefficients. So this is x cubed, so I start with x squared, 1x squared, plus 0x minus 1. Now I simplify, and that's going to be x squared minus 1. Now they want me to completely factor that, which is difference of squares. So that would be x plus 1, x minus 1, and completely factored form is if I would multiply that by x minus 2. So if I would multiply each of these linear factors together, I would end up with my original function.